It's a pleasure to see you all. Thank you for coming to the talk. And like Renata said, I'll be here all week, and hopefully we'll be seeing more of you. Good. So today I'm going to talk to you about a project we've been working on for many years now. Basically, how to measure internet censorship, filtering of different internet protocols on a global scale. Many of the tools we've built here that I'm going to talk about actually enable us to measure internet censorship in hundreds of countries. So this is pretty much the first time that this has been possible. And I'm going to talk about three different techniques that we've used to measure censorship in this way. Before I get into the details, I just want to acknowledge some of the people who've worked on this. So actually started working on this because one of my PhD students, Sam Burnett, was quite interested in the topic. So that's Sam there on the left. He's now working at Google on these topics as well. So he can't tell us what he's working on. But the first part of the talk is a lot of work that's due to Sam and his PhD work. Roya and Safi also was a postdoc at Princeton for the last 2 years and has been working a lot on these topics that I'm going to probably talk about in the second half of the talk. And there are several other people who also worked on the topic. I guess Vern Paxson visited you last year, so he's a very close collaborator on the second half of the talk, the techniques that I'm going to talk about in the second half of the talk. And of course, money, always useful for doing this kind of work, and very grateful to the National Science Foundation and Google for supporting a lot of the work that I'm going to talk to you about today. Good. So censorship is everywhere. Internet censorship. It's in many countries around the world. Depending on the reports you read, of course, they're the famous countries that do this. I probably don't even need to name them, but depending on the reports you read from the Open Net Initiative, the Department of State in the United States, Freedom on the Net report, the Berkman Center, at least 60, 70 countries they'll talk about, sort of at least from the anecdote perspective. And when you read those reports, actually, as an internet measurement person, I was, the first thing I noticed beyond just the number of countries that they talk about is actually there are no measurements. So that actually reading those reports inspired me to really think about this topic. So really, for the first time, we can now measure, we can get data about censorship filtering of different kinds, different techniques in hundreds of countries around the world on a global scale. We can do it in some of these cases. For the techniques that I'm going to talk about, we can do it continuously. So I'm going to talk about some other techniques that have existed in the past. They're either not global, meaning you can get things from very specific vantage points, but not across an entire country. You also, the existing techniques have made it tough to get the data all the time. Okay, so I'll talk about why that's the case as I get into the details. But the main thing to take away from this talk is that the techniques I'm going to talk about, of which there are three different techniques, make it possible to basically get data about filtering of internet protocols, DNS, TCP/IP, and the web, globally and continuously. Okay, so of course the first thing we need to sort of talk about and understand before I get into the details of the measurements is what is internet censorship. It means different things to different people, but it's always nice to start with a plot. This one is not mine, but I don't know if anyone recognizes this plot. Anybody? Okay. Any guesses? Okay, so on the y-axis, this is internet traffic. On the x-axis, this is time. Close. So this was 2011, January 2011, the Egypt internet disruption. This was a case where the government made some directives basically to just shut off all internet traffic, all routes. So this was a route implemented in internet routing. I'll show you a graph of that in a couple slides.
When?
2011, January 2011. lasted actually several days, almost a week. This one I think probably maybe people paying more attention to recently, right? So there was DNS censorship. So this one was implemented with routing. This one was implemented with DNS. So I don't know if that photo means anything to anybody. Does anyone recognize, anyone know the significance of that? That's Google's DNS. So what happened in this particular instance was the DNS, so the censorship was implemented with DNS. So the Turkish ISPs were basically returning, in the response to DNS lookups, block pages or proxies in the country that would implement filtering. So we're going to look at actually both of these. We're going to look at both filtering on the TCP/IP level as well as filtering on the DNS level, second part of the talk. Of course, there are these incidents, and then they're the sort of famous bad actors, but also even in the U.S., actually, this type of censorship filtering can actually be implemented on obviously much more fine-grained scale, but we do see websites being blocked in response to law enforcement. Sometimes actually there was a case of a request to shut down social media during a protest. So this has happened in the U.S., in Britain, Australia as well, many places. The Open Net Initiative, they're a group that studies this. It's a civil society organization. They put out reports on this, and you can see some of the statistics here and anecdotes. Lots of different reasons, obviously, that censorship takes place. And I picked out 3 examples here. You can see the headlines. And I picked out 3 examples from countries that we don't often talk about when we talk about censorship. But just to illustrate that this problem is not just isolated to specific, infamous countries. It is widespread. So we do need to be thinking about this really, and when we're talking about measurement, we really want to think about how to do this from everywhere. Okay, so the next thing I want to talk about is what censorship is, what it means. Obviously, the definition, is many different ways to define it. I'm going to start with a very simple definition, where Alice wants to talk to Bob, and there's a censor in the middle, either preventing Bob, typically preventing Bob from talking to Alice. So Bob, in this case, might be a website. Right. Typically, we're going to talk about, and especially in the first part of the talk, we're really going to talk about websites. It could be any internet destination. Now, when we think about censorship and we talk about measurement of censorship, the first thing we think about is blocking of traffic. Right. But the other thing that we consider in our threat model when we talk about measurement of censorship is not only might the censor want to block the traffic, but the censor might also want to punish a user for attempting to communicate with another internet destination. So this is tricky. This actually comes up, so this might be an example. And actually, by the way, I'll mention right now, we don't really know the extent of this threat, but an example might be, would Alice get in trouble for visiting a particular website that's blocked in her country, right? Okay, so that existential threat may be less or greater depending on the country that we're talking about, but it's something we have to consider when we're talking about measurement. Because if we're interested in finding out whether Alice can talk to Bob, we can't just ask Alice if she can talk to Bob necessarily, right? So we have to think about the risks associated with that. So that's going to come up throughout the talk as I talk about measurement. In particular, I'll talk about some ethical considerations that we confronted as well. As I mentioned, one type of censorship, the one that we saw in the Egypt case that I showed you in 2011, basically done with internet routing. Okay, this is actually really like as close as we've seen to a kill switch, right? So in this case, you can see in this plot, this was due to the folks at Renesas who do measurement of internet routing. You can see how many IP prefixes each one of these ISPs is advertising to the rest of the internet over time, and you can see at some point it basically drops to 0. Okay, so one by one, these ISPs basically just stopped advertising routes to the rest of the internet. Okay. Typically, we don't see censorship in this drastic, kind of nature. It's often much more subtle, right? So it could be specific websites, it could be blocking of those websites, it could be redirection of the user, right? So the user attempts to visit a website and they're redirected to a block page or to a local version of the site or through a proxy. Could be implemented with access control lists with the IP protocol, right? So it could be the IP address that's actually the user's prevented from reaching. Could also be manipulation of the domain name system. Okay, so this might be something where I attempt to look up google.com or BBC, and instead of getting the IP address that I should get, I get an address that directs me to a block page, or maybe I don't get any answer at all. So that was the example we saw in the Turkey example. Good. So for the rest of the talk, what I'm going to talk about is how we get a better handle on the state of affairs for these three types of censorship. Okay. So we'll talk a little bit about the current state of the art in measuring internet censorship, and then we'll talk about three different ways we've developed to get a better handle on these three different types of censorship. First system I'm going to talk about is called Encore. It's uses cross-origin requests to measure web filtering. I'll talk about exactly what that means and how it works. Second system actually is using a side channel in the TCP/IP protocol to measure filtering of TCP/IP. And then finally, we'll talk about the DNS manipulation. If there's time, I'll also talk about maybe what I see as the next wave in information control, which is really not just, instead of just filtering, you could of course manipulate and spread propaganda. And I guess the word these days is fake news, but this is much older work than that. So if there's time, I'll spend a few minutes on that at the end and offer some thoughts on what's next. Okay, so where we got motivated to work on this, about 3-4 years ago, we noted, as I already mentioned, that you see a lot of these headlines, right? So these are a couple years old, but obviously could replace them with more frequent ones. But these are happening kind of, these reports are frequent. And as I mentioned, if you look at the OpenNet initiative or other people who study this, you'll see these reports about what's going on supposedly in a particular country, and often those reports or news stories are based on one-off anecdotes, right? So this, particular website is blocked or threatened to be blocked. And the thing that we observed is that knowledge about what's going on in these cases starts with an anecdote, and it often ends with the anecdote, right? So there's no actual data you can go download. There's basically nothing that continues to measure this over time, like how long has it been blocked? Is it just that site? Is it many other sites? So we wanted to basically expand on this to get more than just anecdotes. As people who work in internet measurement, we view this as basically a measurement problem. Okay, so can we get data to help us better understand what's censored, where, when, and how? And by the way, this example here, right? So Twitter censored in Iran, it's 2009, and it's censored with a block page, right? Okay, well, actually we've been moving to get even more fine-grained than that, right? Because as we know, like any country is more than, just one data point, right? There are many ISPs in a single country. We saw that in the Egypt case, right? In that example I showed, there were 5 different ISPs. Even within a country, there can be different politics, different dynamics, etc. So, for example, in China, the political scientists will tell you that the coastal cities have very, very different politics than the western provinces, and they want better data about what's going on as far as access to the internet in these different parts of the country. Okay, so we want more than just anecdotes, and we want continuous measurements at a much finer spatial granularity than we currently have. Okay, so this turns out to be really hard. I mentioned we'd like to do this in as many places as possible, but this is really difficult. Okay, the first challenge, of course, is that for every location you have, of which there are many, you have different languages, different cultures. So actually, if you want data in a particular country or a particular region, until we started doing this work, you pretty much had to either know someone there or send someone there. Okay, so knowing someone there doesn't scale well. Sending someone there doesn't scale well either. That can also be, so you might be able to get a limited number of vantage points for a short period of time, but getting something across, hundreds of data points or hundreds of vantage points inside a country continuously, just not possible. That also brings with it its own set of risks as well. The other issue, of course, is that, as I've already alluded to, there are many different ways that censorship can be implemented, right? So, again, the diversity of how filtering or manipulation or control of access to information, many different ways to do that, which means basically we have to think about designing many different tools to help us get better information about this. Okay, so that's the challenge. How was this done, or how previous to our work, what was the kind of state of the art? Okay, so the basic idea, behind many of the existing frameworks is you get an anecdote, right? There's some story, some reporter or activist or somebody basically says, "Oh, I can't reach Twitter in Iran." Then someone decides maybe it's time to go check that out, so they ask some researcher. This might be someone like you or me. It might be someone happens to know somebody in the country. It might be someone goes to the country, right? But there's a human involved, right? Whose job it is to run some software to try to access Twitter, right? And then they tell you whether or not they succeeded. Okay, so the best known tool that does this today is actually part of the Tor project. Tor is for those of you who don't know, how many people know Tor? Okay, so most people, but for those of you who don't, that's a system for anonymous communication. They also have a lesser known part of the project that is some software that attempts to measure things like reachability of websites and the ability to use Tor from different countries, etc. The way that this works is you basically load their software onto a laptop or a Raspberry Pi, and then you convince someone to run it, and then that piece of software uploads some information about whether or not those attempts to access websites or what have you succeeded or failed. Okay, so there are a whole bunch of these places where it's deployed. They have some measurements from different places. You can see some places more than others. And the main thing to take away from this is that they've been doing this for many years. They really don't have very many measurements and not very many places. Okay, so nice idea, difficult to scale up in practice. Okay, so in fact, when we started working on this, this was how we thought we'd approach it as well. And then the student I mentioned, Sam, realized that actually getting deployments in hundreds of countries over time was going to cause him to not be able to graduate in any reasonable period of time. So we came up with a different idea. And the idea, for those of you who are sort of familiar with how ads load on web pages, the mechanism is quite similar to that. Okay, so here's how this works. Instead of sending the researcher to the country, we have the researcher install software on a website that they either control or they can get a volunteer to install their script on. Okay, so we've sort of turned the problem around so that now instead of the researcher needing to deploy vantage points in lots of countries, they deploy an endpoint, right, that other vantage points might visit. Okay, so now every web browser is going to become a potential vantage point. Okay, now the way this works is if some vantage point, some user in that country visits this volunteer website, that website basically contains a little snippet of code. I've shown it to you here in a 0 by 0 iframe, and when the browser loads that, basically there's a script that causes the browser to basically try to access a third party. I'll get into the details of that in just a minute, but that's the basic idea. Simple in principle, complicated for many reasons. And I'll talk about both the technical and non-technical complications to this. So what did we do? So the contributions of this work really is a technique for measuring web filtering at scale. We built an emulation testbed to actually show that this works, and we released the software. It's, by the way, still running. So it's installed, I think, on about 10 or 12 different websites, and we're still collecting data based on this. So so I've talked a little bit about the motivation already. Let me sort of just kind of review a little bit, like web censorship, how, web filtering, different ways that web filtering could be implemented. Then I'll talk in a little bit more detail about how the tool works. And then I'll also talk about, I'll briefly mention how evaluation, and then talk about user risk, in other words, the ethics of ethical considerations of doing this. Okay. So if a censor wants to censor Twitter, there are various ways, of course, that one could do that, right? So if a user is trying to access the site, there's a DNS lookup, right? There's a TCP connection, and then on top of that, there's basically a web request. So three different opportunities. So at the DNS level, there could be return no such domain, could drop the request. You could actually inject a fraudulent response, a reverse path. For IP, you could basically reset the connection in various ways. You could send a reset. You could drop the attempt to connect. And then at the HTTP or the URL level, you could, again, drop the GET request. You could do a 302 redirect. Many different ways to do this. Okay, so what we'd like to do is detect that something is fishy with a web request, and then, if possible, try to figure out more about the mechanism that's being used to cause the request to fail. Okay. So I mentioned briefly already how this works at a high level. Let me dig one level deeper, and then we'll go one level deeper than that. But here's the basic idea. So there's let's say, for example, we're interested in answering the question, is Twitter censored in Iran? Okay, so suppose there's a web browser in Iran, right? Okay, and if that web browser happens to visit a site where Encore is installed, which, as I mentioned, there are about 10 or 12 of these. In addition to loading the site, the browser basically loads a script, which then basically asks, basically the browser is going to load that iframe I showed you, and that iframe contains a script that basically triggers an additional object request. Okay, that's called a cross-origin request. I don't know how many people are familiar with web security model. Few? Okay, good. So I'll define origin in the next slide, but basically what this means is you're asking the web browser to fetch an object from a third party. Okay. So good. Either that thing that I've circled in red succeeds or fails. Okay, so this is good. Now good in a way, like we've basically have a mechanism to turn that web browser into a measurement vantage point, because we can ask that browser to try to load this, and either it works or it doesn't. Okay, so there's some catches to this. One is technical. Okay, so for those of you who know a little bit about web security and privacy, you may have heard of this thing called the same origin policy. Okay, so the web privacy model, or web security model, has this thing called the same origin policy. So an origin, in the context of the web, is a tuple. It's the protocol, so that's HTTP or HTTPS. It's the host name, so twitter.com, and the port. So if it's unencrypted, that's port 80. If it's HTTPS, that'd be 443. Okay, so together, that three tuple defines an origin. So here's the trick, right? Is that web browsers prevent one origin from reading data from another origin, right? So that would be called a cross-origin data read. So for example, if one origin is ours, right, Encore, then over here we cannot read anything that basically has been requested or loaded from another origin. So the browser basically assembles all those objects together to assemble the page. But different origins cannot read content from other origins. So what that means, so I've listed some examples here of things where those reads are prevented. What that means in our context, right, is we can ask the browser to load something else, but we can't actually read what actually came back. Okay, so that's actually a little bit of a problem for us, right? Because we wanted to know whether or not that worked. Okay, so some limitations, right? Means we can't actually see what got loaded. Okay, so there's certain things we can't tell, right? If it's totally different content, then there's no way we can figure that out. However, if all we're interested in figuring out is did the request succeed or fail, there are side channels that allow us to do that. Okay, so if all we need to know is not reading the data, but in fact just did that URL load successfully, then the restrictions on that kind of leakage is actually a bit looser. So the image tags, the style sheets tag, iframe, etc., many of them have callbacks. So for example, the image tag has an onload and an on error directives, and you can use those basically to, so for example, we can ask, we can embed an image tag that basically triggers the cross-origin load, or a style sheet or an iframe. And if that object load succeeds, we can get the browser to tell us, right, through that callback, right? So we know basically whether or not, based on the outcome of that callback, whether or not the load succeeded or failed. Okay, so with that one bit, we can try to get a little bit more, we can try to use that to get more inference on exactly what's going on, right? So we could try to load many different images from twitter.com, right? If some of them, if none of them load, right, then we might infer that this is domain level. If some of them load, right, then we might infer that something's going on at an object level. Similarly, we can try things that basically resolve to the same IP but have different domains, and if those are failing, then we might infer that the blocking is at the IP level. Okay, we're going to do a little bit better than this in the second half of the talk, but those are the types of things that you can infer by loading different sets of objects.
Just a question. So here, if they put a fake page, or if they,
we have no way of knowing.
You don't know.
No way of knowing. Yeah. So so this technique will not help you at all for that. I won't say not at all, but it's complicated. It would not automatically tell you anything useful. Okay, so I'm not going to get into all the evaluation, but these are the things that we evaluated in the paper. To what extent does this work across browsers, platforms, different types of filtering? Can we observe real instances? Which types of sites can we measure, and what's the overhead? Okay, so I'm going to talk a little bit about the first two based on an initial set of data. So we've been running this now for more than 3 years. So when we published the paper, we had about 6 or 8 months of data based on a deployment actually set on 17 different websites. And we got measurements, as you can see, from 170 different countries. So this is like unprecedented. Okay. Yeah.
So what kind of websites?
What kind of websites did we deploy it on?
Yeah, because you have to convince the...
Yeah, so these are all researchers. So like I installed it, some other researchers installed it.
And do you still get enough hits from these countries to be able to evaluate?
That's an excellent question. So as you might imagine, actually it's interesting. This is an excellent observation. This is a drawback of this tool that the other tools I'll talk about don't have. But this one we actually depend on those websites, those browsers visiting the sites where this is installed. So ideally, this would get installed on a popular website, and then we'd have everything from everywhere. But yes, we are limited by who's visiting those websites. Fortunately, for I guess academic researchers in the U.S. especially, I don't know about France, but certainly in the U.S. we get a lot of interest from Chinese students and Iranian students, and at least we did in 2014. So interestingly enough, I guess a lot of the countries where students are interested in coming from actually happen to also be some of the famous actors. Happy coincidence in this case. But no, you're totally right. We're actually limited in that sense. The other thing we're limited in with this tool, since we're on the topic, is we can't control when we get the measurements. So for example, one of the things that we were interested in seeing was like what's going on during the Iranian election. Well, we can't just fire up the tool, right? We have to wait for people to visit the site. So obviously, this really hinges on being deployed on sites where people actually are visiting frequently. Yeah, excellent question.
Sorry, it is deployed in France?
Is it deployed in, is it on a web server here in France?
Yes.
Don't know, actually. I can't remember. I don't think so.
Okay.
Yeah.
And in particular in Nuria?
I don't think so. Yeah.
Okay, thank you.
Yeah.
If I'm connecting through a VPN or impact or conclusion?
If you're from a VPN, like, then we would basically measure the reachability from the VPN endpoint. Yeah.
Can you pay Google as Google Ads in order to embed your iframe to get more people?
Excellent question. Yeah. So we actually, so the question is, can you basically deploy this through an ad network? And the answer is yes, you can, sort of. And in fact, there have been some follow-up papers that have done exactly that. Actually, a number of people have followed up with things like that. There's a little bit, we thought of it at the time when we tried it. One of the issues is that some of the ad networks limit what you can do as far as like deploying JavaScript. Right, so we basically need to serve JavaScript for this. So some of the shadier ad networks actually let you serve JavaScript, but Google does not. So at least not at the time we were doing this. But people have followed up with this. In fact, some people who are interested in measuring like IPv6 deployment and reachability. Jeff Houston and others in Australia are basically doing this type of thing with an ad network. Yeah, great question.
Maybe this kind of solution also is another problem for the webmasters because they may be detected. Is there a way for the countries that do censorship to detect that this webmaster allows the detection of censorship in this country?
Yeah. So could the website be blocked because they're discovered, to be running this tool? Good question. It is possible. I think with the deployment of HTTPS, it makes it a little more difficult to do what you said. Of course, even that's not going to be perfect because the SNI and the DNS are going to be still in the clear. So that wouldn't be perfect, but yeah, it's a potentially a concern. Yeah, good question.
Just one more question.
Sure.
How do you decide the tests that you're going to have the browser do?
Oh, yeah, good question. So actually, I should skip ahead. Why don't I skip ahead to that? Because that actually is this. So the question is, we can ask the browser to load any website, right? So how do we basically test, how do we decide which websites we want the browser to test? Right. So there are lists of well-known sites that are frequently blocked. The Citizen Lab, it's out of the University of Toronto, maintains an extensive list of these. The Berkman Center at Harvard also has a list. We started off by some of those lists contain things like porn and other things that you probably don't want to be triggering. So we initially removed that stuff, and then we figured the rest would be okay. And then the long story short, because we only have 22 minutes, is that it's probably not okay. And what we basically boiled this down to is if you get into the sort of lingo of ethics, there's different ways of reasoning about risk. Okay, so there's something that we basically. So let me come to the practical question first. So the only sites we basically measure right now are Twitter, Facebook, and YouTube. And why did we limit it to those? It comes down to this principle of, it's called the principle of minimal additional risk. So here's the idea, is that it's pretty hard to browse the web these days without actually loading one of those sites. Okay, because there are Facebook like buttons and Twitter share buttons. Pretty much any website you go to is likely to trigger you know, a lookup or an object request to one of those sites. So based on that, one can reason that basically we are not introducing significant additional risk by triggering a browser to make a request to one of those sites. Get into details of like, could we expand that list? The answer is yes, probably, but yeah, that's probably a longer discussion. So that's what I wanted to say about Encore. Let me talk about the other two in the remaining time. So this is, these are both, yes.
One question.
Yes.
Do you know whether Encore has been targeted for censorship, like whether it's been added to IP block list, which would kind of stop requests from getting to you?
Not to my knowledge. I mean, we're still basically getting measurements, so not to my knowledge, but certainly it could very well. We have not taken any steps to make it more robust, and it certainly could be an easy target. Yeah. There are ways around that as well. The paper actually talks about how you could make it more robust to blocking, but yeah, that's a longer discussion. Okay, let me talk in the remaining time about some other follow-up work we've done looking at both IP and DNS-based blocking. So TCP/IP, is that familiar to everybody? Yeah, okay. So we all know the TCP handshake. Let me just review the upper right, of course, is probably very familiar, right? If a port is closed, you get a reset. Okay. The bottom right is also important to remember. If we send a TCP SYN and the port status is open, right? If there's an open port, you get a SYN-ACK. If you don't reply with the ACK, you continue to get SYN-ACKs. Okay, so that particular feature of TCP/IP is going to be important for us. Okay, so let me come to, okay, so here's I'm going to get into the details here in a sequence of slides, so I'm not going to go over everything on this slide right now in gory detail, but I'm just going to give you the main trick. Okay, so the trick is any machine, including routers, right, when they generate packets to send, will in the IP packet there's the IP ID, the identifier, right? So this is a vestige of fragmentation. If you remember, IP packets could be fragmented before MTU, path MTU discovery. We had these issues. The IP ID is still there, and typically it increments. So if a machine sends a packet, it will have an IP ID value. If a machine sends another packet, it will have the next IP ID value, typically one greater than the previous one, et cetera, et cetera, et cetera. Now, that IP ID will increment, right, as new packets get generated. And different versions of the operating system will increment that in different ways. Okay, so one way to do it is I've got a counter, right, for each TCP flow. Okay. The other way to do it is I just have one counter, right, and every packet I generate, regardless of which flow that packet goes to, right, just increments the same counter. So we'll call that a global counter for the IP ID. And if those are the ones we're interested in, the machines that have a global counter, okay, it'll become clear in just a minute why. Okay, so we're going to call that a global IP ID counter, one counter for any packet the machine generates, regardless of where it's headed. Okay. The basic idea is if you can find machines that have that property, you can induce that machine to generate packets, right? Okay, I'm going to talk about how, but right, we know how to cause a machine to send a packet back to us in many different ways. We're going to use TCP, right? In this case, we send a SYN, right? That machine's going to send a SYN-ACK, okay? If we spoof where the SYN is coming from, we can get that machine to try to send SYN-ACKs elsewhere, right? Once we do that, now the SYN-ACK is going between two places that we don't control either endpoint, but now I can start to infer things about the reachability between those two endpoints. So that's the basic idea. This system is called Augur. Before I get into the details of the IP ID increment, just a few requirements. So we need three pieces to this system. One is a measurement machine. That's the place where I'm going to send my TCP SYNs from. Right? From there, from that location, right? In this case, it's in the United States. Where's my mouse? Okay. Okay. From this location, the only thing we need is the ability to send packets with spoofed source IP address. Okay. So what I'm going to start doing from that machine is sending TCP SYN packets with a spoofed source IP address. Okay. Then if the country, let's say in this case we've got China there, right? I'm interested in measuring from, right? So this is Alice, right? Trying to talk to Bob. I need to find a machine in that country that has this global IP-ID property, okay? And then the place I'm interested in measuring to, like the website, for example, which I'll call a site, okay? I need to find a machine that has an open port. Typically, if it's a website, that's easy enough, right? Port 80 works. But basically, I need it to be open so that I get that SYNAC, the SYNACs coming back. That property where the SYNAC retries come is actually going to be important for us, right? Because that's going to cause an increment in the IP-ID counter that we can actually see. Okay. Now, there's blocking in a couple different directions. Right, and we want to see disambiguate both directions. But before I get to that, let me just let's talk about what would happen in the case where there's just no blocking. Okay, so we've got our measurement machine. It's going to send us, So we're going to send a SYNAC, right? And this basically what we're going to do initially is try to get a sense for what the IP-ID value is at this machine inside the country where we're interested in measuring reachability from. So we're going to basically get, see how that counter value is incrementing. For various reasons, we basically look at at the rate at which that counter is incrementing. Okay, so we're going to basically get a baseline for that. So we're going to see resets coming back with different IP-ID values, and we're going to see how that value is moving over time. Okay, reason we want to see that, right? So it's moving, because presumably it's talking to other places on the internet. We're going to try to perturb that, right? So we're going to try to accelerate it. Okay, and whether or not it accelerates is going to tell us something about reachability. Okay, so if there's no blocking going on, then the next thing, so we get a baseline measurement for the reflector, right? Then what we're going to do is spoof a TCP SYN packet, and we're going to make it appear that SYN came from our reflector machine over here. So the SYNAC's basically going to go that way. Okay. Okay. The reflector's going to say, hey, wait a minute. Don't know who you are. Please go away. Send the reset. No problem. That's going to cause the IP-ID to increment, right? So by step 3, we basically cause this machine over here to increment its IP-ID. If we do this, this is simplified, right, because it's just one packet. But you can imagine we send enough of those, we can cause a perturbation that we can actually observe. So we can come back at step 6, right, and say, what's your IP-ID? And now we can see, is that accelerated in a way that we can actually tell the difference? Okay. So this is obviously, that's the basic idea, right, is we can try to perturb the IP-ID counter. And if there's no blocking, we'll basically see an acceleration. If there's blocking, right, then we're going to see different types of effects. So let's suppose that there's blocking in this direction, inbound. I'll call this inbound, right? So from Sweden or what have you into China is blocked. Okay, so what would happen in that case? Well, same thing happens in step 1, 2, and 3. Step 4, the SYNAC, right, tries to go back, like, because we're spoofing with this reflector over here, right, the SYNACs try to go back over here, but they're blocked. Well, what happens when the SYNAC gets blocked, right? It keeps trying, right? So that's where the retry comes in. Okay. Good. If the blocking happens in the other direction, right, then we basically get that SYNAC basically makes it through, but we get a reset, right? And that we can basically observe here as an increment in the IP-ID counter here. Okay, so in summary, right, depending on the direction that this blocking is occurring, so if it's basically outbound, right, so from the reflector to the site, we're going to basically see increments due to those resets retrying, right? If it's inbound, right, then we're going to see IPID increment with the SYN-ACK retries over here that we can measure at the site. Okay, so that's the basic idea. Yeah.
So how do you identify machines where you can do this spoof SYN package? Because lots of those might be blocked too.
Which one? So let's go.
Measurement machines
Yeah.
where you should be able to send a spoof.
How do we identify these?
Yeah.
Yeah, those are hard to come by. Fortunately, we only need one of them. Right, so it's us, basically. It's actually really tough. This one, I think we're using a machine at Berkeley. It was really tough to get, though, actually, because it's harder to spoof on the internet than you might imagine. Fortunately, we don't need very many of those, right? We just need one. So, because once we get one, we can send to lots of reflectors and lots of different sites, which is what we do. Good. So I think in the interest of time, I will skip the statistics here. But just to give you a basic flavor of this is a maximum likelihood detection problem, right? And the random variable is the IPID acceleration. So we basically detect so our prior is like, did we perturb or not, right? Did we inject those spoof SYNs or did we not? And we basically measure the IPID acceleration over time, and we try to figure out basically, is that acceleration due to our perturbation, or is it just basically no effect? So that's the basic technique that we use. I think I'll also skip over the results of basically where we're seeing blocking, except maybe I'll just show you one highlight. So this is basically the percentage of, so again, the numbers here aren't particularly fascinating, and that's the paper has more details about like which sites are blocked. This, of course, is a function of which sites we test, which comes back to the earlier question. For this one, there are also ethical considerations in this work, right? Because if I go back to my picture here, we are inducing a machine inside the country of interest to send packets. Now, whether or not sending a TCP SYN is incriminating or not, could be open for discussion, but we'd like to basically avoid any potential implication of a user. What we do in this case is make sure we're hitting routers, okay, as opposed to end host machines. And I won't get into the details of how we do that, but that's basically that's the approach we take here, is to try to hit infrastructure. Because we're relatively confident we're measuring from infrastructure machines, that gives us a little more latitude in terms of the sites we measure to. So for this study, we used the Citizen Lab block list. So we used the hundreds of different websites, and this was of that block list, what percentage of the sites that we measured off that list were filtered. And you can see the usual suspects sort of popping out of the heat map here. I guess that's all I'll say about that for now. Okay, so with the remaining time, I'll just talk a little bit about DNS. Okay, the last way that we've been trying to measure manipulation or filtering on a global scale. Okay, so DNS. You're probably familiar with, but here's the trick. Okay, so here's the basic setup, right? We do a DNS lookup. It goes through a sequence of authoritative name servers, et cetera, et cetera. This is probably all familiar. And the only thing I think to sort of remember for the purposes of this talk is that it's not secure. Okay, so any kind of manipulation can occur. I mentioned a few earlier, right? There you could return no such domain, when in fact there is a domain. You could inject, right? So if there's a sensor on path here, the sensor could see the query and race to give a bogus response, etc. Okay, so what we'd like to do is detect cases where client is basically trying to look up a legitimate domain or domain and gets an IP address that isn't the one that we would expect it to be. Sounds easy enough, okay? The infrastructure that we use in this case is we use open DNS resolvers. So that terminology refers to a DNS resolver that will basically resolve queries. It's one of these. but it won't check who you are. Like typically a DNS resolver, for example, in this building will probably check to make sure that you're on the local network before answering your query. There are something like 20 million DNS resolvers around the internet that will basically answer to anybody. Okay. Now, there's an ethical complication with those as well, is that of those 20 million, a large fraction of them are sitting in home networks, and we don't want to use those. So skipping over some details there, we pruned that list very aggressively using other people's measurements of the internet topology to try to basically prune down to DNS resolvers that are not sitting at the edge of the network, but are in ISPs. Is that perfect? No, it's not. Still those could belong to individual users, but it's a lot better than using things that are clearly in homes. That takes our list of 20 million open DNS resolvers down to about 5,000. But fortunately, those 5,000 are still in about 180 countries. Okay, so we still have pretty good coverage, even if we're just restricting ourselves to those 5,000. Okay, so once we have open DNS resolvers, the question that we're interested in is simple, right? We just want to find instances where the IP address that our resolver returns isn't the right answer. Okay, now the only problem is that there's often not a single right answer. So this is a picture from the USC project that tried to basically map the Google infrastructure, and you basically look up google.com from different places around the world, and you basically get IP addresses that are all around the world. So this is really tricky, right? Because the first way that you'd think about doing this is like, well, I want to go into country X and I want to do a DNS lookup for that domain, and if I get an IP address that's sitting in that country, that's going to be fishy, right? Except no, because often there are local caches in that country, right? So what we want to do is basically figure out that we're not talking about this case, that we're actually talking about something that's inconsistent but weird. Okay, so there are two different ways that we do this. Actually, there are two different classes of techniques we use to do this. One is we basically look at different consistency metrics. So the idea here, obviously IP addresses are going to come back different, but if we map those IPs to autonomous systems, right, the ISP, if you will, hopefully we're going to get the same ISP in a lot of those cases. As a matter of fact, we do, and that's the most reliable consistency feature. We also looked at three other different ways of doing this. One is you get the IP address and you fetch the web content, okay, and you see, is the content the same, right? So you can look at for consistency of the content. You can also you get the IP address. You can try to fetch. You can do a TLS handshake, get the certificate, right? So you can see if I fetch. I get this IP address here. I get a different one over here, but if I fetch the certificate from those two different places, if it's the same website or the same organization, hopefully I'm going to get the same certificate, right? Or at least the same organization. You can also try to take that IP address and do a PTR lookup, right, to turn that IP address into a name. That doesn't always work, but it's another trick that you can use, right, if you try to reverse map the IPs, like they go back to organizations, and we can see if are those organizations the same. We take a very, very conservative view of consistency to say that if any one of these passes, right, if any one of these looks consistent, then we say, it's maybe okay. Okay. In addition to consistency, we also there are things that we can verify independently, right? So we can look at the content of if the IP is serving a certificate for that domain, we can see does the certificate returned, is it actually correct? Does it actually refer to the domain that we fetched? And is it signed by a certificate that the browser actually trusts? Okay, and there are different ways you can do that. So interestingly, for those of you, and I think there may be some who've looked at TLS and HTTP certificates in the ecosystem, as it turns out, consistency is a better metric than this one because many people screw up the configuration of HTTPS. To basically sort of illustrate the effectiveness of these, without explaining the metric in detail, further to the right on this plot is sort of more effective, right? So it's more often that we get a correct or consistent response when there's no manipulation occurring. Okay, so you can see basically that for our control domains, like most of the time you're getting the same AS. And then basically, a lot of time you get the same IP address. Sometimes you don't, obviously, in cases where there's a CDN involved, right? Even when there's a CDN involved, it may be anycasted, so sometimes we do get the same IP address for those. You don't always get the same HTTP page. Sometimes you do. Sometimes you don't, because there might be regionalization, right? But a lot of times you do, right? So you can kind of go down the list here. And this is sort of what I mentioned. So same cert, right? So the same cert is the next sort of most effective, and you can kind of see that the correct cert, right, is further over on the right of this. This is what I was mentioning before. Okay, so the manipulations basically occurring in the usual suspects. Now, this plot, we probably need to think about better ways to present this, but it is what it is right now. So blue is basically, you know, the number of measurements we took in that country. Okay, so we took more measurements in the U.S. just because there were more open resolvers that we could use in the U.S. Red is basically the number of the proportion of responses that we got in that country that were manipulated. So most of our queries were in the U.S. We did, and there's some fraction of our queries were in Iran, and of the queries that we made in Iran, 40% of them basically failed on all of those tests that I mentioned. Okay, last slide before I conclude. So this basically shows by different countries. Each point is basically a domain name. Okay. Each vertical bar here is a country, so let's just focus on one country. Each one of these points is a domain name. Let's focus on the pluses. Those are the top 25 domain, Alexa top 25 in that country. The height, or the y-axis, is the fraction of responses, right? When we did a bunch of queries for that domain from lots of different resolvers, open resolvers in that country, the fraction of samples that we got back that indicated manipulation, in which case the fraction of responses for which all those tests failed. So interesting things going on here, and this really poses more questions than it answers, okay? So if you had asked me before we started this what I would have expected to see, I would have expected to see all or nothing, right? Either 100% filtered or not filtered. And instead, we're seeing this weird heterogeneous kind of thing where like 80% of the time we're getting things that are manipulated. So that's strange. And this points me to the next, sort of the next step of the work, which is that, is this measurement artifact? Is it a function of like different ISPs doing different things? Is this probabilistic? There have been some censorship studies that have suggested that censorship might be probabilistic. Is this a political calculation, right? Sometimes on, sometimes off. We don't really know. So there are a whole bunch of different questions that now we're sort of talking with political scientists about the types of things that they want to know. And some of them are here. I'll just read off a couple and then we'll finish. But basically, they're interested in variation, right? So, within a regime, right? Do you see different, different things going on, within a country? Are there certain periods of time, like political anniversaries, where you see different types of behavior? Are there, triggers? If something happens in Hong Kong, and therefore, like that sets off something in China. So these are things that basically we just don't know yet. But hopefully we can get to the point of answering. And then, what types of things do we see, and then can we use those types of measurements to explain better what's actually going on? So we've been doing this, as I mentioned, for 4 or 5 years now, but I think we're really just at the beginning, right? For the first time now, we've got a bunch of different methods where we can get a bunch of data all the time from hundreds of different countries. The data is not perfect. In many cases, it's statistical. Lots of work left to do, but lots of interesting questions that we can study together. So thank you. Sure.
That's a question. So you've studied this for some years now. It's something like the Great Firewall of China, for instance.
Yeah.
Does it use all of the different censorship methods? So what's more prevalent?
So it uses a bunch of different. It's basically a bunch of different methods. So something I didn't talk about specifically here is like they're known to use things like keyword filtering. That's become more difficult now with HTTPS, right? With more of the web becoming encrypted, they're not able to. So the traditional technique was like look for keywords and then reset the TCP connection in both directions. So that was interesting. People were able to measure that for many years because they'd reset the connection in both directions. So you could actually send a request inbound, right, with a keyword and then see the reset come back at you from outside the country. That one's become more difficult now because with encryption becoming more pervasive, they've had, now they're basically doing this DNS manipulation. We've seen that actually. So a different study I didn't talk about. We were able to uncover some examples of DNS proxies doing injection on path. So that's widely used. IP access controlless filtering also is known to be used. So IP and DNS are pretty common. Yeah. Yeah.
Can you have a comment on the magnitude of the violation in countries that are supposed to be, free countries like US and France? Which are, the rates that you've shown are significant for those countries.
Yeah. Yeah.
So,
like more than 1%, right?
Yeah. Which is already.
Yeah. So I think basically we're just at the tip of the iceberg here. So let me give some examples, right? So one thing that some of those maybe are like inside of businesses or companies, right? So that might be one example where some of those are happening. Another is like sometimes it's not political or news sites, but it's like gambling or some other thing that's basically prevented from a particular organization in that country, and it's not a countrywide kind of thing. So those are some examples where we've definitely seen those things turn up, but yeah, there's some that we can't yet explain. Yeah.
Did you correlate your results with political events like elections? For instance, I saw that you measure France and Romania, and there were recent elections there. So your measurements were during the election period, out of the election period. It was correlated with the daytime, nighttime.
Right. So the web filtering we've been doing for quite some time now, and as I mentioned, that is limited because we can't trigger the measurements. We have to wait for people to come to us. These other two pieces of work we've really just completed this year, and this summer we're starting the continuous measurements. So not yet.
Okay.
Yeah, yeah, but it's coming.
We're covering the just previous results we presented.
Yeah.
What was the period?
Oh, this one.
No,
1 week.
It's 1 week.
Yeah, that's 1 week.
Which date?
Let's see. That was 1 week in February 2017. I forget the exact dates, but it was early February 2017. Yeah.
In this talk, the definition of censorship is an attack to the protocol infrastructure between layer 3 and layer.
Yeah, it's blocking of reachability in this case.
Manipulation of returned results of Google or other search engines, because if you don't know that it is there, you will not reach the document.
Yeah, we have not. Actually, we've studied that a little bit as well. That was one thing that I didn't have time to talk about at length. But one thing that we've done is look for consistency of search results across geography. That's really tough to get a handle on, because separating personalization from regionalization is tricky. You can do things like start with clean user profiles and stay logged out. And then you still can see effects of regionalization, but that's obviously not what most of us are. That's not the way most of us are browsing either. So it's a good question, and I don't have a great answer for you yet. Yeah.
This was about the blocking information. What about reversing, so augmenting the fraction of information of some sort?
Adding information.
Yeah. So changing the proportions.
Like,
So if I have a search engine, for instance, I can accept censorship, not blocking information, but increasing the share of certain information.
oh, so like adding more.
If you pretend you're clicking to a page, that's what you mean.
No, but exposing more pages which point to some content.
Mm-hmm. Like publishing more. Yeah. We have not looked at that. It's a good question. Yeah. Yeah.
Okay, we should probably wrap up, and then if people have questions, we'll make some of your own. Thank you
Yeah.
again.
Okay, great.